So now we'll move into number 7. Okay, so we're now at section number 7. Okay, so like section 6 is just a recap on specifically defining the empirical method, because we'll go back to it. And now we are about to go like into like an example. So number 7 is an example of the rigid and flexible pavement empirical design. So I just wanted to refresh you guys on what the empirical method is. Okay, so we're going to be designing a new flexible pavement for a major interstate highway using the following conditions. We'll start with a flexible pavement example. Okay, let's get into it. So these are your design parameters. The pavement location is urban. Pavement function is an interstate. Number of lanes is 3 lanes in each direction. That's 6 lanes in total. Traffic distribution, you assume 80% of the loading occurs in the design lane. Annual growth 2%. Design period, investigate 20, 30, and 40 years. Construction materials, they're given here. As you can see, I'm not going to read through all of them, but yeah. The construction materials are given right there. Okay. So then subgrade. Okay. So the subgrade, that's the MR, that's MR. So these are the subgrade in the dry months, in their dry season, and in the wet months. Okay. So this is the, funny enough, their dry season and their wet season coincide with the dry and wet season for New Zealand and South Africa. It's very interesting. So the overall serviceability loss, the reliability, traffic count, so the double unit trucks, and the truck trains. So these are all the parameters you need. Then we move on. And then so the solution. So by looking at several different design periods and reliability levels, this example gives an ideal relative influence of the design inputs. Right, work can be verified by using flexible pavement structural design utility. So the ESL per year. So this step involves converting the daily traffic volume into annual ESL amounts, pavements that are typically designed for critical lane or the design lane, which accounts for the traffic distribution. So the ESLs per year equals to vehicles per day times lane distribution factor times days per year and ESL vehicles. This you'd know from traffic engineering or transport engineering. So for single, this is what you'll get. For the double, this is for the trains, this is what you'll get. So this will be the total, then you round up. So this is your ESLs per year. So you can just have a table like this and just punch in the calculations. As you can see there, all the calculations are there. I've done most of the heavy lifting for you guys. You multiply and just make sure that that's correct. So yeah, let's move on. Right? And then the standard design multiplier to calculate the compound growth multiplier here. So for your 20-year design life, for your 30-year design life, for your 40-year design life. So you guys, I would expect you guys to be following with me as I'm going through. So yeah. And this is what you're supposed to get. Let's move on. And then you come to the big equation. So then you calculate the effective subgrade support using this equation. So you punch in everything and you find out, remember we said our W18, that's the predicted. So you check if your predicted is close to what you guys got. If it's not, you go back and do the process until W18 is now closer to what you predicted previously in the previous slide. That's the objective. So when those numbers are within 5% of each other, you got it. So it's, simple, like easy peasy lemon squeezy. I think that's what they say in America. Yeah, it's simple, very simple, very, very, very simple. So that's all you need to do. And then you get your answer. So let's move on and see what we'll get in our final analysis. Okay. So here you can see this is what you'll get, your ESL designs, and you'll have your SN, your SNs, your SNs, as you can see here. Based on the reliability, the thickness of each layer, this is what you're going to get. So in the end, your calculation, you must have a table like this, very simple. So the idea is when you have a table like this in your report, now for reporting purposes, right, you can then, you see you've given the client options, and then you can have also a table with the cost, right? So you can say for, let's say, a 20-year design life, right, the cost per kilometer is going to be, these are just random numbers. I don't really know how much road costs to construct in in America, but okay, let me give an example of in South Africa. So I would be saying a 20-year design road will cost 1.5 million per kilometer. For a 30-year design life, it will cost 2.1 million per kilometer. For a 40-year design life, it will cost 3.4 million per kilometer. And this is a 16 kilometer road. So now you're just going to say 16 multiplied by 1.5. So you can give them different options on the budget. So then they can go back and then, you know, if it's a municipality or if it's Department of Transport, right? They can say, okay, our budget is 30 million, right? So if our budget is 30 million, right? Or our budget is 40 million, right? Our budget is 40 million, okay? Our budget is 40 million, right? So we want to see what we can afford, right? So then what they'll do is they'll say 1.5 times 20. They'll see that's 30 million. So they can afford to design it for a 20-year design life. Then they'll say times, let's say it's going to be what, 2.1 for 30 years, right? They'll see that's 63 million. That's way out of budget. So what they'll do is they might come back and ask, can you make it a 25-year design life, right? 25-year design life, most probably will go up to 40, 41, 42, right? So then they'll say, okay, our budget is 40, but we can, obviously we have that plus or minus 10% contingent, right? So we can stretch it up to 44 mil. So can you then design it for a 25-year design life? So when you're right, so that's how you would present it to the client. This then now goes into stakeholder engagement, which is very important as an engineer. So the objective of having this tabulated like this is it enables you to communicate to the client exactly, and it enables you to go through something that we call design optimization. So you can then optimize your design depending on your client's budget, because in the end, we need this to be constructible. Most definitely, we need it to be constructible. So the objective is to be able for your client to be able to make money from this, you know. So that's what we would be going through. So that is what we would be aiming for. In the end, this is the end result that we want, and we can be able to communicate to our client exactly what they're going to get. We're telling them how much bang they'll get for each buck. And then that interaction can help the client. And then you become a better engineer because you are in touch with your client's desires. You're not just designing in a silo. So stakeholder engagement is very important. So that, and the client will thank you because they can then say, okay, no, maybe we might be able to ask for more funds because we want it to be 30 years. Okay, since you said 30 years is 60 mil and our budget can only stretch up to 45, they have enough time to go through the, because you know, bureaucratic processes take time. They have enough time to be able to go through the processes of acquiring those additional funds so that the project can go on. So this is very important to be able to represent. And this is so, it's so simple, clear cut. You don't need to be a civil engineer to understand this. So I would add an additional table to say that for the 20 years at this is going to be the cost. This is going to be the cost. This is going to be the cost. And then, yeah, Bob's your uncle. And then that's done. So, yeah. Let's go into our last slide, which would be the end of this chapter. Let me say of this section, let me not say of this section, but of the section for the design pavement for flexible pavement. So in this particular example, which was only shown for one set of a possible solution for an HMA surface course and the base course layer depth, we were kept constant, and the HMA binder course depth was varied depending on the requirements. Notice also that a change in reliability level from 90 to 90% results in an SN increasing from about 1 and a resultant increase in the HMA thickness from about 55 millimeters. It is interesting to know that in most empirical design procedures, HMA, no matter what the specific mix design or size, is treated equally. Here, the 12.5 millimeter super wave surface course and 25 millimeter dense granular binder are also structurally equivalent. Okay, so that's just a conclusion on the design layers, but yeah. And also you could see that reliability was also, you know, going down. So you can tell them for a 20-year this reliability, and you can also divide it into the reliabilities to say this will be the cost. So it actually gives your client more information, and they can make a more informed decision as the client. You give them all the tools to make an informed decision, and that actually makes you a better consultant. So that is the basis of being able to present your results or your findings like that. Okay, so let's move on to the second example, which is an example for rigid pavement. Okay, so for the rigid pavement example, these are the design parameters. I've spoken about them. So in this case, you are to design a new rigid pavement for a major interstate highway using the following conditions. It's an interstate, it's a 3-lane, you assume 80%. Then the only difference is the construction material here. You're assuming your PCC, those are the uh, compression, maximum compression, so 5.17, which is actually very reasonable. Then that's the load transfer, your J. Then the overall service loss, the reliability, so various reliabilities, and then your void, that's that, the drainage coefficient, the loss of support, and you're just taking it as one. Like I said, typically you should take it as one, and the traffic count. You've been given the traffic count data, which is actually really good because sometimes you have to go and do your own traffic count, which actually sucks because you're outside with the traffic counters and it's hot. Yeah, I've had some bad experiences with that, but yeah, anyhow, moving on. So then you go through the design ESLs, you calculate that. With that goes without saying. So then you calculate the effective modulus of the subgrade reaction K. This calculation is a multi-step process, right? So in the AASHTO guidelines for the design of the pavement structure, the basic steps are as follows, okay? So you determine the roadbed resilient modulus and the subgrade elastic modulus and use these values along with the projected slab thickness to graphically determine a composite modulus of the subgrade reaction K, right? You modify this K to account for the effect of rigid foundation near the surface. The idea for doing this is that the subgrade will offer a greater support if the rigid foundation, right, like a bedrock, is located near the surface, of course. Then you determine how this modified composite modulus of subgrade reaction K, or the K value, varies through the typical year. Typically is done by season, so wet and dry. Then using the projected slab thickness and modulus of subgrade reaction that has been modified to account for the effects of rigid foundation near the surface, you use a graph to determine the relative influence of the various K values throughout the year will have on the pavement performance, right? Lower values of K indicate less support and are potentially more damaging than higher values of K indicating more support. Therefore, the lower values of K are weighted more heavily in determining the weighted average. Okay. Then after that, you correct the weighted average K to account for the potential loss of support arising from the sub-base erosion. Then sub-base material that are more prone to eroding will result in a larger downward correction for the K value, and this can be determined in step number 4. So for calculating your MR, your sub-base MR, your composite K, and your relative damage, you use the graphs, the associated graphs, right, from the guide, right? And most steps involve graphical solutions. Although these graphs are not produced here, a summary result of the table can be shown. So I'm not gonna go through all the graphs, unfortunately, because that'll most probably take way too much time. So what I then expect you guys to do is when you're carrying out this example, I expect you guys to have already downloaded the guide since I've spoken, a lot about it. You have the guide open when you're going through this example. You're able to extrapolate all the relevant tables and all the relevant data. You must come up to a table like this. So this should be your end product, right? So you must be able to work around everything until you get this table. If you guys want a breakdown of how to carry out everything, like a total design and how to program a spreadsheet, just let me know in the comments, then I'll make a course for it, and then you guys can go through that course, or I can take you guys through that course. Not a problem at all. But since this is an introduction and I'm trying to touch on everything, there's no utility in me now starting to break down everything, but I'm just going to give you what you're supposed to get. So this is what you're supposed to get, and if you don't get this, you're making a mistake somewhere. Go through the guide, understand the guide, go through everything that we've been through, and try and understand what I'm trying to get at. Okay. So based on the results from the AASHTO guide, right? Based on that figure 3.6 from the guide of pavement structural loss support 1.0, the K efficient is 250. Like I said, I expect you guys to have the guide, or at least to have access to the guide because it's there online. Use the 1930 Ashto empirical equation. Using this previously calculated ESL results and the 19 Ashto empirical rigid pavement design equations, the following. So this is the what we'll get. So these are our final results. So you have your 20 years, you have your PPC surface course for different courses, the years, and different reliability, like I said. So everything is clear cut, and then you can make a cost estimate for each option, and then your client can choose exactly what they can afford or what's in their budget, and they can forecast and plan how they want to carry out construction and in an organized manner, because that's the objective. The objective of designing is so that the things can be constructed. We're not designing for fun. We're trying to provide services to the public. We're trying to provide civil engineering services to the public, and we're trying to enhance the built environment. So it just goes back into what I was saying before. So this is what you'll get. What I'll do is, now that we will talk about it, I'll actually add to the course documents, I'll add the 1993 AASHTO guide so that you guys don't have to look for it. You guys might struggle. So I think I'll add all the documents, even the South African guidelines, the New Zealand guidelines. I'll add all of that so that you guys can just download them. So it doesn't really matter if you're in South Africa, you're in Australia, you're in New Zealand. You can then be able to go through those guides and be able to understand. So in other series, I'll focus on South African design methods, then I'll focus on New Zealand design methods, and then I'll focus on the American design method. But I feel like for this series, we focus mainly on the American design method because this is the mother of all design methods. So this is the inception of how we design pavements empirically, or using design guides, or even mechanistically. So it was very important to touch on this because all those other guides reference the AASHTO methodology of design. So now when I'm doing those courses, if you've done this course, it then makes sense. You have a basis. You have a base already, and you understand where it comes from. You're not just complying, because there's a tendency in the engineering field where people just comply and you don't really know where it comes from and you don't question it, and that's when it happens, when sometimes you make mistakes or you use the wrong methodology. Anyhow, let's finish up this section. Particular example which only shows one set of possible solutions. The HMA base course and the crushed stone course layer depths were kept constant, and the PPC surface and course depth was varied depending upon the requirements. You notice that the level from 90 to 99% results in PC slab thickness increasing by about 50 millimeters. The 308 mm thick slab shown for the 40-year design life reliability is probably nearer to the maximum practical slab thickness for highway. Yeah, because it also needs to be practical. So you're not going to design a slab for 500 millimeters, half a meter thick slab. That's insane. Like it's not feasible. It's too expensive. The reinforcement would be large. It's not. So which is why I'm saying, when you provide these options, then you provide the prices automatically. If your design is now going into 100 million to design 16 kilometers of road, or I don't know, 10 miles of road somewhere there. I think 16 kilometers is about 10 miles or slightly less than 10 miles of road. It makes no sense to design a 10-mile road for 100 mil. That makes logically it makes no sense. So all of that will guide you, which is why you have to tabulate it, and then you can start eliminating, so that's the idea of having your tabulated results. You can eliminate the results that don't seem to make any practical sense. Or these are things where also your supervisor will then guide you to say, we can't make a half a meter thick slab for a road. Way too expensive and practical. It's going to be very heavy. So all of that practicality, because it also needs to be constructible. So it all talks to each other. So yeah, that's also very important to look at. Yeah. So that is all for chapter number 7. I will see you guys in chapter number 8.